Okay, let's continue. So, we have our electrons around a nucleus that contains most of the mass of the atom. Okay, so there's a problem here that even Rutherford recognized. And it's this idea that if the proton is, or the nucleus, because they really hadn't gone into protons and neutrons yet, but if the nucleus is positive and the electrons are negative, then what's keeping the electrons from just falling into the nucleus, right? Why are they continuing to orbit or fly around it? Why isn't it not just eventually kind of going in and falling in? Okay, so another experiment. We have these tubes, okay, filled with different gases of different elements. And we have a way of connecting these tubes to high voltage. So we're going to be supplying a whole bunch of energy to the atoms contained in this gas. And when we do that, something really unique would happen. I think we call them now like spectral tubes. Anyways, so we would get certain colors of light being emitted depending on the element that it was. It almost seemed like the color of light being emitted was unique to the element of the gas that was composed there. And so we see this colored light being emitted when we would excite the atoms of a gas, by adding high voltage. And then we took, a slit of this colored light and passed it through a prism. And instead of seeing a continuous spectrum like we would with sunlight, if we took sunlight and we took a tiny little, strip of sunlight and we passed it through a prism, we don't see distinct lines or colors of distinct lines. We see a continuous transition from one color to the next. It's not interrupted. But this color light was. It was very specific lines of colored light. Okay, remember, energy of the photon is directly related to the frequency of the photon. And so frequency dictates the color of the light, right? Shorter wavelengths, which means higher frequency, is in that blue-violet range, and then the longer wavelengths, lower frequency, that was in the orange-red part of the spectrum. So that must mean that the light being emitted by this gas was not photons all throughout, but photons with very specific energies. And that's why we saw very specific frequencies. That we were not getting photons being emitted from this gas that had an energy that was in between here. Okay? They weren't being detected, they weren't seen. So, what must be going on then? Bohr comes along and he has this idea that energy, that electrons exist, reside within specific energy levels, that they can't exist in between these energy levels. They're not going to transition from one to another. They instantly jump and then instantly fall back down to lower ones. And that solves this problem of electrons falling into the nucleus because they can't exist in between those energy levels, which was supported by that wave component, right, of electrons. That in order, if electrons have a specific frequency, that they can create a standing wave with that specific energy or frequency, and so they can stay residing in that energy level. But if they have a frequency that is higher or lower, then a standing wave, it will interfere with itself. The wave will destructively interfere, it'll cancel itself out. And then we'll find another frequency, which means another energy level that these electrons can exist at. And so they're never going to be in between. They're never going to have an energy that's in between. They're going to either be at this energy level or that one, or maybe one above it or below it. Okay, so that's what our Bohr model is showing us. The Bohr model is not showing us the location necessarily of an electron. It's a representation of the energy of these electrons. Okay? The further away you move from the nucleus, the greater energy that is gained. Okay? So these energy levels that are close to the nucleus, these are low energy. And then energy levels that are above, these are higher energy. But why would that be? Let's see. So, if we have a negative electron and a positive nucleus, they want to be close together. There's an electrostatic attraction, right? And if we pull that nucleus or that electron away from the nucleus, we have to add energy to do that, right? We have to pull them apart. So in order to get this to move at a higher energy level, we have to add energy for it to get there. But then we don't have to add energy. We don't have to push them back together. They'll naturally want to be closer to one another because that electrostatic attraction. Lower energy usually means stability. Okay, so if we can lower our energy, we can become more stable. Okay. So Bohr proposed that hydrogen atoms have only certain allowable energy levels. So he correctly predicted the frequency lines of the atomic emission spectra. So he correctly was able to mathematically predict what these colors would be. And then the lowest allowable energy state of an atom is called the ground state. And when the atom gains energy, it'll go to excited states. Okay. All right. If I'm adding energy, and remember I was doing this with high voltage, I was adding energy to these atoms. So I'm going to add energy to these atoms, and what I'm really adding energy to in the atom is the electron. So I'm going to add energy to the electron, but the electron cannot exist in between these energy levels. So let's say I add enough energy to this electron that it can jump up to this energy level. So it now exists at this energy level. But it's going to want to gain that stability. Eventually it's going to want to go back down. In order to decrease in energy, that energy has to go somewhere. Energy cannot be created nor destroyed, but it can be transferred into something else or translated into a different type of energy. And so what happens, so amazing, that these electrons would jump back down in an energy level, and in order to do that, they would emit a photon. And these photons must have very specific energies because these electrons are making very specific changes or jumps in energy. So we have to lose the precise amount of energy to go from this energy level to that one. And so we would get a photon that was emitted with that change in energy. And again, I'm just showing a 2-level jump, but it doesn't have to be that, right? We could have an electron going from the third one to the second one, or we could have an electron going from the first one, the second one down to the first one. Okay, there's all these possible, and this is not the end of the energy levels. There's more beyond that. So we have these transitions that are happening, and each transition results in a unique change in energy. And if that's a unique change in energy, that means there's a unique photon being emitted, and so we get these specific colors then. Okay, we learned that in chemistry, whether we remember it or not. And we took this idea and we said that the energy of the photon that's being emitted must equal the change in energy. So if I do the change in energy of this electron, because in order to make that change, it has to emit a photon of equal energy. This would be the energy of the higher energy level minus the energy of the lower one. Okay? And again, that change in energy is going to be equal to the energy of the photon emitted. And we have an equation for energy of a photon, which was Planck's constant, multiplied by the frequency of that photon. Okay? So the change in energy of the electron is what's going to determine the frequency of the photon that it emits. Okay? That's what we did last year. Is I gave you the energy levels. I told you like what this energy level of N3 was, and I told you what N1 was, and you subtracted them, and then you could figure out that was the energy of the photon, and so we could find the frequency. Now, we're going to take this one step further. Instead of me providing this information for you, there is a relatively simple equation to derive it. Okay, let's look at that. Okay, don't get overwhelmed by these. Okay, we're not going to focus on these. This is the equation we're working with. Okay, so energy of the energy level, meaning the energy of the electron at that energy level, where the ground state, the energy level closest to the nucleus is in n equals 1. So n equals 2, n equals 3, etc. That will equal negative, because our electrons, right, are negatively charged. So we have this negative 13.6 electron volts times by 1 divided by the energy level number that we're working with. Oh, there's a name for that. Oh, that's going to drive me nuts. These n values directly correlate to the energy level of the electron. And so that is the energy level that's associated with the period on the periodic table. I'm trying to blank on that name. Oh well, I'll remember it. So we have, let's run this. Let's see, what if, where are we at time-wise? Okay, we're going to start on this. We have a hydrogen atom. We're going to determine the energy of the innermost energy level. So we want to figure out what the energy is of n equals 1. The energy level of the second one, n equals 2. And the energy difference between the first and the second. Okay? And then we'll figure out what we would expect the wavelength to be of the photon emitted. So let's start by figuring out this energy and that energy. Okay, so our equation is the energy level is going to be negative 13.6 eV. Okay, we'll say this is, we'll do 1 first. Multiplied by 1 divided by our n number, which in this case is 1 squared. Okay. And we're going to do the same thing for n equals 2. This will be that same kind of constant value, 1 divided by 2 squared this time. Okay, so we're going to get these numbers, and then we're going to find that difference between them. But let's convert them to volts, or sorry, to joules first. Okay, so you're going to get final answers here that are in electron volts, and then the conversion factor from electron volts to joules 1 electron volt is the same thing as 1.60218 times 10 to the negative 19 joules.